awesome guests as well. And so we'll do some deep dives on some of the leading open source models. Before that, minor logistics, this is being recorded. So yes, this is being recorded. You can access it at the link afterwards, and we'll also put it up on YouTube in a day or two. As the webinar is going on, the format that we'll do is we'll do quick intros. We'll do 15-ish minutes from each group, and then go into general Q&A. So as you have questions that arise, I'll be monitoring the chat, but please put them in the Q&A box on the right. So if you can see, there's a chat section, which most of you are probably in, and then there's a little box with a question mark under it called Q&A. You can not only put questions there, but you can also upvote them. So upvote the ones that you most want to see answered, and we'll go through those in that order at the end. There's lots of stuff in LangChain. Today, we're going to mostly be focused on, or we're going to be entirely focused on open source LLMs and what that means. And obviously, that actually probably touches every component of LangChain, but in so much as we can keep the questions and discussion focused on open source LLMs, let's definitely do that. We have a really unique opportunity here to learn from some of the best in the game. So with that, maybe we can start with some introductions. Brandon, do you want to start?
Yeah, sure. Hi, everyone. My name is Brandon. I am the founder and CEO of Nomic, and today I'm going to be talking to you guys about GPT-for-all, how Nomic thinks about open source, a little bit about open data, and stuff like this.
Awesome. And then Daniel, do you want to go?
Yeah, so hi, I'm Daniel. I'm a machine learning engineer at MosaicML. I mostly work on our composer and streaming and LLM Foundry libraries, so kind of our whole like training runtime. Yeah, great to be here. Thanks for having us, Harrison.
Thanks for joining. And last but not least.
Great. Yeah, thanks, Harrison. Nice to meet you, Brandon. And yeah, thanks for joining, everyone. I think my name is Bandish. Actually manage the ML engineering team at Mosaic. And I'm going to be tag teaming with Daniel today to talk about our open source LLM and our training and inference stack.
Awesome. So as you can tell, we've got some awesome guests, and we'll start off with Brandon doing a deep dive on Nomic and GPT-for-all and lots of good stuff. So take it away.
Thank you. Let me just share my screen. All right, looks like you all can see that. Hopefully you all can see that. As I said, my name is Brandon. I'm from Nomic, and today I'm going to be talking to you a little bit about explainable and accessible AI. And the reason I'm going to talk to you about this is it's really Nomic's goal to improve the explainability and accessibility of AI. And while explainability and accessibility might seem like they are distinct concepts at first, and indeed, like each has their own sort of like particulars to them, we at Nomic see them as having a very important intersection. And the way that we think about these ideas, I think, is pretty well illustrated in this Venn diagram. So on one side here, we have the explainability piece where we're doing things like analyzing training data of models, modeling interventions we make there, observing their outputs. On the other side, we have the accessibility piece, building models that can run in low resource environments or can run in sort of like privacy constrained environments. But really what we see as the intersection of these two things is, a set of sort of criteria, open documentation, open code, open weights, open data, that we sort of broadly call open source AI. And so, looking at open source AI as the intersection of sort of like explainability and accessibility, I think is really one of the core reasons why Nomic is really interested in moving that forward. And one question you might ask is what makes a model, open source? There are a ton of models out there nowadays. They've all maybe got different subsets of them open sourced. So perhaps an architecture, but no data. Perhaps you have only a subset of the weights, perhaps no weights at all. Maybe you don't have documentation, but we propose sort of a 4-item checklist to, kind of guess and check yourself about, okay, like, is this model sort of actually open source? The easiest thing to sort of open source, the least stringent requirement we think is open documentation. So this is, a model card or a tech report or a paper, ideally with a methods section. Not that any major AI lab would release a tech report without a methods section that describes, what is happening in your model. Not only is this critical for like accessibility because it lets people understand your method, but it's critical for explainability because without knowing what the system is doing, it's going to be very hard to understand when you should use it and debug it. Going sort of beyond this, we then get into open code. And the observation here is open docs are often insufficient. For those of you that have been around in the AI sphere for long enough, you'll remember the sort of like pre versus post layer norm discussion that was occurring, where there was some documentation that showed that the layer norm was in one place in a transformer, but if you actually looked at the code, it turned out it was in another place. There was, some questions around where it should actually go. And the only way that you can actually resolve questions like this is by diving into the code. So, again, like critical for the explainability access or sort of aspect in terms of trying to figure out what's actually going on. The next thing is open weights, right? So the observation here is a lot of models are going to be tested on some benchmark data set. It is probably going to be the case that there's a mismatch between that benchmark data set and whatever you want to use the model on downstream, or however that model is being deployed. Often it's just like the LM evaluation harness or something like this, or like Helm maybe. But really the question that practitioners should be asking is, how does this model perform in my operating domain? And so open weights gives us the ability to actually like test these models on particular operating domains that are, task specific, which is sort of critical for responsibly deploying these things. And then the last thing that I want to comment here on is open data. What we have found at Nomic, and I think what Mosaic will agree on, maybe they'll comment on it in their presentation, is the idea that the training data itself really dictates a lot of the behavior of these models. And so having some kind of open training data is really going to, one, improve your ability to understand like why a model is behaving in certain ways. And two, it's going to allow you to, properly attribute that model's maybe behaviors or ideas back to the training data itself. Again, not that any major AI lab would systematically pirate training data from the entire internet for their own profit. But anyway, this is sort of how we think about whether or not a model is open source. And now I'm going to go into a little bit around, once you have these open source components, how might you use them to maybe explain a model? And then a little bit, how might you improve accessibility with them? So the first thing that we look at Nomic is, training data analysis. And I actually have a meme from Cody from Mosaic on the right here, which I think sums up the situation pretty well, where really like there seems to be this resistance to actually like looking at your training data, but it gives you such an outsized ability to understand what is happening in your model. And Nomic wanted to make it sort of as easy and painless as possible to really dive in and explore your training data. And so we built Atlas as a tool to try and make that as simple as possible. Atlas interface in a second, but we're going to do so through a case study of the Koala model, which is this open source model from Bear. So looking at our checklist, like, yeah, great, they have the model, it's open, they have some documentation on it. But one thing that you'll see is under the section, the method section where they talk about how they trained it, you can see they trained it on the Anthropic HH dataset. And when you dive into the code, what you see that they did is they actually ran causal language model on the chosen responses of this dataset. And this is a dataset that we've mapped with Atlas in the past. So here's the Anthropic HH dataset. All of the colors correspond to clusters, and then the words are sort of like semantic labels that we've extracted using GPT-for-all from those clusters. And one of the things that pops out to us immediately is like this area up here that says racism. Like that might be something we don't want to train on. So if we zoom in and maybe look at something adjacent to it, which is this sort of like insult cluster, one of the things that we'll end up finding is there's this sort of like dialogue here where the model says something like saying offensive things, and like clearly that's not something that we actually want to teach our model. So we shouldn't really be doing causal language modeling on these phrases. There's a lot worse stuff in this data set that I can't put up on screen right now, but I invite you to go and look through it for yourself. The reason why it's in this data set is a little bit subtle. It's because this data set isn't for language modeling. It's for building reward models for RLHF. But regardless, what the open data aspect of the koala model allows us to do is like pinpoint the fact that there is toxic data that has been used to train it, and then perhaps resolve that for future model trains. That would not be possible if you didn't actually have, the open data portion of it. I'm going to skip the Lion example for now, just from a time perspective. Another thing that you might care about here is once you have identified maybe some bad data in your training set, to understand the effect of removing it. This is some speculative work that we've done recently in collaboration with Johns Hopkins, where we trained 2 language models. One is a baseline that's trained, on a bunch of classes from an encyclopedia, be it, plants and animals and art. And one of them is trained but never sees any articles about plants. And what we found is that inside of this plant ablated model, not only are the representations of plants affected, but we see sort of this bleed effect where removing plants from the training data also affects the representations of animals in natural places. And so we are super interested in trying to understand, like, 4 different mixes of training data, how these, bleed sort of like effects end up sort of like coming to be, and like how they interact. And then, again, there's this idea as well of observability of these models. So we talked a little bit before about like having open weights so that you can actually test these things on your operating domain. Often that operating domain changes over time, and a lot of your errors will generally be, traced back to a shift in that sort of operating domain. What you see on the right here is an atlas map of Twitter, and we sort of like filter it out and show you how that evolves over time. And yeah.
Your screen might be a bit frozen, so your screen share might have been a bit frozen, so might want to retry.
Uh-oh. That's not good.
Yeah, And now it's gone. So
yeah, I turned it off. Let's see. Can you guys see now? Potentially.
Can't see anything.
Uh-oh. Apologies, everybody. Can you at least hear me? Am I coming through okay?
Yeah, you're a little bit blurry. The audio is fine. The video is a bit blurry. There's some speculation that that Atlas Nomic thing is taking up all your CPU power, so you might want to close that tab. I don't know if that's true or not.
I think it's my bad hotel Wi-Fi is the situation here. Let's see. Yeah, apologies for the technical difficulties. Oh dear. Here, give me 1 second.
No worries.
Goodbye, camera. We have moved to the I am tethering on my phone part of the life here. So hopefully that will work. All right, how are we looking?
I can see your screen.
Cool. I will skip ahead here just for the sake of time then, and we'll finish up. All right, thanks everyone for bearing with me while we handle the Wi-Fi issues. Anyway, so the whole point of that being open training data, very, very critical for sort of like explainability in these models. The other thing I'm going to talk to you today about is accessible AI. And we sort of think of this in Nomic in 2 kind of buckets: low resource and private models. So one of the first things that you can do to kind of understand the importance of low resource models is posit a couple of axioms and then derive a theorem from it. The axioms that we follow are one, people with access to these models are going to far economically outpace those without access to them. And the second axiom is there's large populations of people that don't have access to the compute required to run these models. I think anyone in this chat that's tried to provision a GPU in the last 6 months will know how hard it is to even get something even get a GPU. And that is, as someone that can pay $25 an hour for maybe, an 8x8100, right? And so if you want to mitigate the risk of differential access to this technology, you need to develop systems that can run on limited compute. And one of the proudest moments for me personally in sort of like building Nomic was when I first saw this graph on the right, which is the geographic breakdown of our Discord server. And we saw that the largest sort of like geography represented was other, which I think really means that we're able to bring this technology, to a lot of places that might not have necessarily the compute access that we do. So I think that is going to be really critical for the adoption of this technology. And the other thing that these low resource models kind of enable is the idea of privacy. So, right now, if you want to use GPT-4, you send all of your data to OpenAI, and then they promise not to train on it, much in the same way that they promised that they were actually a nonprofit like 5 years ago. And so if you want to do that, that's great. But if you don't, what you're going to probably want is something like an air-gapped system. And because you might not have, say, access to the latest and greatest GPU technology, you can have those air-gapped systems be enabled by the ability to run these models on sort of like low resource hardware. And, the Samsung story that maybe we've all heard at this point, where they leaked a bunch of, notes and source code is sort of like the first of what I imagine will be many cautionary tales about what happens when you actually sort of get put this data out into the wild. And then to conclude here, for the sake of time, people might ask us what's next. I think the closest thing that we have to releasing is adding the Falcon 7B model to the ecosystem. So if you're looking, if you're watching us closely, you'll see that one of our awesome engineers, Aaron, opened this pull request last week, adding, compressed, GGML support to Falcon 7B. So be on the lookout for that in the GPT for All ecosystem soon. Anyway, thank you guys, and happy to take any questions at the end.
Awesome. Thanks for that. I have one question kind of at the, what's been the, and this is around kind of like the Atlas thing that you showed earlier. So I think one of the use cases you mentioned was like finding kind of like pockets of data that you might want to I guess like what are the main use cases you see people using kind of like Atlas for, specifically when kind of like is it like they use it as a step before they train the models, or they use it as a step when they're validating other models that have been trained? Like how and if so, for either of those, like what are the main like pockets of data that you see people being like really interested in?
Yeah, so we see it all over the place. We think of Atlas very much just as a tool for exploring large unstructured data sets. Training data sets happen to be of that type. The data sets produced by models also happen to be of that type. And so it's applicable in both cases. In terms of like the actual specific use cases, we'll see one, what I showed today, which is the idea of going through your training data, understanding the composition, understanding if you have things that are toxic in there. You have the ability to like layer metadata on top of it, which helps in terms of like trying to understand what filters on top of your data might be doing. And so, some of the work that we did with Lion, let me tempt fate here and maybe try and share my screen as an answer to this question. So this is 15 million images from the Lion data set, and we worked with them to really try and understand.
I think we may have tempted fate too much there.
Color by the not safe for work score. And one of the things that we helped them find is they had this failure mode where there were. Oh dear. Well, c'est la vie.
It worked for a little bit. We got a quick view of it.
All right. Hopefully you saw the sort of like hotspots popping up on the map for the not safe for work score. And those hotspots allowed us to sort of like investigate what is happening along the decision boundaries. There are a couple of errors that we helped them find. So we see it for the sort of like data quality and sort of like filtering step as well.
Awesome. Awesome. All right. Let's move on to the next one. Mosaic, you guys are up. What do you got for us?
Oh, wrong button. That's how I'm going to lead off. 1 second. All right. You guys see the screen?
Yep.
All right, great. Yeah, so thanks again, Harrison, for having us here. My name is Bandish, as we mentioned before, and I'm going to be tag teaming this with Daniel. I'm going to talk to you a little bit about our motivation. Why does Mosaic exist, and why we actually decided to train a large language model and open source it. I'm going to hand it off to Daniel, talk about the science and engineering that went into and some of the decision making that went into training that model, and I have the pleasure of playing the next slide game. And then after that, I think I'll take it back and give you a quick overview of the actual tooling that we use to train the model. So I think first motivation, right? Like, I think brief history lesson, I think this is all within the last year or so, but I think the real question we all wanted to ask ourselves is like, does one language model really rule them all, right? Like, are we going to live in a world where only a few companies that have the money, the expertise, the compute to train these large models, just in a few large foundational models that are very capable? Is that the world that we want to live in? We don't think so at Mosaic. And we actually think that there's probably a place for both. But we believe in the contrary. We believe that numerous high utility AI systems are going to emerge. We believe that companies will want to create their own moats by training their own model. We also believe this will be more cost effective to kind of train your own model, deploy it. And remember, cost here includes both training and deployment costs, right? So it's actually important to kind of look at both of those hand in hand. And I think there's a whole body of evidence kind of showing this, right? Thought leaders are also kind of arguing that, hey, like high value workflows are definitely going to be addressed by specialized AI systems, not necessarily general purpose ones. So I think there's a lot of kind of traction here. And this is a great place for us to kind of make a big impact. And so the future we believe in is kind of one for both. We think that there's going to be a lot of folks out there that can probably just buy an external API for some use cases and go develop applications around it. And I think LangChain has done an amazing job kind of enabling people in this space. And the area that we're going to also be focusing on is enabling people to build their own models and deploy their own models. So I'm going to talk a little bit about what we're offering in both of these spaces. But yeah, I think this is where we're really headed. The problem with this is that the perception is still that building your own language models is really hard. It's expensive. It requires a lot of compute. There were numbers being thrown around that training GPT-3 costs like $5 to $12 million at some point. That's huge, right? That's a major capital expenditure for a lot of people. But we're here to kind of bust this myth, right? The reality is different. Training LLM models is accessible, and we've already seen a lot of use cases for this, and we've seen a lot of instances of this. For example, just a few weeks ago, Replit, with a very small team, 2 engineers, trained a model less than 100K on the MosaicML platform. This is a leading code completion model, and it beat Codex. There's been other instances of, for example, Bloomberg GPT outperforming other financial NLP tasks. And of course, the folks over at Stanford, who built a model that, performs very similar to Text DaVinci 3, but being small, and some of these, weren't commercially licensable. And I'll kind of talk about that in terms of MosaicML. But this is happening, right? This is not an impossibility. So what did we do? At the end of the day, we built this great platform. We have some open source tooling to build and train these platforms, train these models rather. But really, we had to train a model, right? We had to demonstrate that we can do this. The proof is in the pudding, so we decided to give the world a taste of the pudding. So what we've released so far is an MPT 7 billion think about it maybe as a demo of what's possible on the MosaicML platform. We actually released 4 models. The first is the base model. We also fine-tuned 3 other models, right? A chat model, an instruct model, and a story writer model. And story writer has been very popular. I'm sure there are folks who have played with this. It's got a massive 65K context length. We used Alibi for that. And first thing we did is fed in the Great Gatsby and generated a new epilogue, right? And so, and what's amazing about this is the base model just took 10 days and about $200,000 to train. And it's commercially friendly license. So you can start using this with your business. You can start deploying these models. And you can start fine tuning this. Along with the model, we also released the LLM Foundry, which is our kind of large language training stack. And basically it's using the same exact tooling that we used to train MPT 7 billion. So we've seen great traction. And there's been a lot of amazing talks. Some folks have worked on making it multimodal. There's awesome, great tutorials, and I think there's also a great tutorial about how to work with MPT 7 billion with LangChain. And so let me kind of stop there. I know I kind of flew through that, but I'll hand it over to Daniel and actually kind of get to the meat of the presentation, which is the science and engineering behind training this open source model.
Yeah, so I'm going to talk a bit about what went into creating MPT 7B. So there are kind of 3 main components that I'll talk about a little bit: the data, the algorithms and architecture, and then kind of like the infrastructure for training it. So next slide. So the data mix, as Brandon was talking about, is very important for the final model that you get. And there's still like a ton of science to do here for sure. So we started kind of with the pre-training mix from various published works. So that's like a mix of some like common crawl data and some other higher quality, maybe more domain specific data like archive, GitHub, Wikipedia. And then we did a bunch of experiments at smaller model scales to kind of tune this mix a little bit and get a better idea of how different subsets impacted the outcomes. And a few interesting decisions to call out. We decided to focus on English for this model, where we don't have like multilingual experts, and a lot of this is like looking at the data, looking at the models, playing with them. And so we decided to focus on English for this one. And then we also found in our early experiments that repeating data is not the end of the world, as maybe some papers and some the general kind of idea may have been. So we repeated some of these smaller data sets up to a small number of times to ultimately get to our 1 trillion data mix. And then at the end of the day, there was a little bit of intuition thrown into it as well. We were pretty sure we wanted a model that was good at some other stuff like code and had world knowledge. And so there was a little bit of intuition in deciding the final data mix. And over time, we'll get better at the science side of it and hopefully rely a little bit less on the intuition. So next slide. The next thing I'll talk about a little bit is some of the model architecture and like training choices. So the first one that is kind of front and center, especially with the long context model, is that we chose to use Alibi, which allows us to dynamically extend the context length. There's a bunch of science, again, still to do about like how much the model actually uses the whole long context length and all of that. But it does remove kind of like the first technical blocker to playing with a long context model. And we also found that using Alibi actually produced better models and more stable training runs. So those were 2 other kind of key factors in choosing Alibi. And then for the optimizer, Atom is probably the most popular one. While we were leading up to training this model, the Lion optimizer came out, and we ran some experiments very quickly and found that it had no performance degradation relative to Atom, but it has a much smaller memory footprint. So it was kind of strictly a win for us. So we went with that. And then the last thing is kind of part of this, maybe like a little bit of myth busting that Bandish was talking about. For all of our models so far, we have only used FSDP. So that's fully sharded data parallel. There's no tensor parallelism. There's no pipeline parallelism. And this means that the code is much simpler, first of all, and much more accessible to extend and read. and also kind of helps us improve iteration velocity. So I've talked about kind of all about all these experiments and the model. Yeah, sorry, next slide, thanks. But what is it that kind of lets us do all of this easily? So we've worked really hard to build good software and infrastructure to do experiments and good science and reliably produce models. And we've talked a bunch about it in our blog, so I encourage you to check that out. But it's also very important for us because this is the stack that our customers are using, and this is also our open source stack. So all of the code that we use to train GPT-7B, Bandish will talk a little bit about the difference between the open source stack and our platform, but all of the main driving code components are open source. And there's a bunch of nice stuff in all of that open source code. I'll just mention a few of the things that kind of are important to doing these experiments. So one is easily allowing us to stream in data from Cloud Object Store in different mixes. So on the left, there's what one of our YAMLs looks like with a mixture of C4, Markdown, and MC4 in a deterministic way. Another is we have our own evaluation harness that we run during our training runs. So we do ICL, in-context learning, evaluation live during the training run, so we can kind of get a better idea of how things are changing and how the training run is going. That's hopefully a little more informative than just looking at the loss curve. And then next slide, the last thing I'll mention here is that with the Mosaic platform, we have automatic resumption from hardware failures. So this image is essentially our logbook for the GPT-7B run. We just turned it on and then watched it for a while and then turned it off when it was done. And this cost about $200,000, as Bandish said, over 10 days on 440 A100s. And everything, so again, everything here except for the GPUs and the orchestration, so this automatic resumption from hardware failures is open. Everything else is open source. And I'll hand it back to Bandish to kind of discuss the components of that stack a little bit more and close with what's coming next and how you can get involved if you're interested in kind of working with our open source tools or models.
Great, thanks a lot, Daniel. Yeah, so I think the first thing that we need is great tooling, right? I think if you looked at kind of the previous loss curve where you're looking at our almost seamless resumption, right? I mean, we are seeing failures, right? Hardware fails, things happen, someone messes up a setting. Being able to stop, resume quickly, being able to start where you left off is really important. And so, we went and built a software stack that can do all of this. So I think there's kind of on the left here, we're trying to depict what your typical ML training stack will look like. I think the main thing here missing is sort of the experiment trackers, but it's the same as kind of like a box there somewhere. But yeah, you have your user code, your data loading and processing tooling, you have your distributed training framework, whether that's vanilla PyTorch code or some kind of more fancy thing like PyTorch Lightning or Fast AI. You have your deep learning libraries like PyTorch or TensorFlow. And then when you're running on multiple GPUs, you need some type of deployment, orchestration, and then obviously the completely complex software ecosystem of device driver and toolkits and tooling and all the fancy version mismatches and things like that you have to deal with. So how do we kind of address this at Mosaic? Well, one of the first things we actually built, and this was right when the company was very new, is we built Composer. Originally, we built Composer as a training library. It was actually built to facilitate a lot of our algorithmic research and algorithmic efficiency research. So it has a lot of amazing features there. It's actually an optimized PyTorch trainer at the end of the day. Supports multi-node training, checkpointing to object stores, and it also logs to your favorite experiment trackers, right? So whether you're using weights and biases, TensorFlow, MLflow, anything that you really want. And it's also very extensible. So it's easy to add new things. We have a two-way callback system that lets you easily modify what's happening in the training loop. So we kind of built all this for research and then realized this was a really, really great way to also start using to train large language models. So it's such a very core part of the LLM Foundry. In addition to that, we kind of realized we need to go where the compute is, right? When we were starting the company, whether we can get V100s on AWS or A100s somewhere else or wherever, And what we really kind of found out is the data kind of anchors you. And so what we ended up doing is building this streaming datasets library. And what this does is enabling high performance streaming from any cloud object store. And so you can stuff your data set in an R2 bucket somewhere and stream it, with zero egress fees to AWS or OCI or GCP. It really kind of gives you flexibility to run anywhere. And the other thing that streaming lets you do is very fast resumption, right? So we don't have to deal with spending hours or days even spinning our data loader when we have to resume a run. We can kind of just pick up very quickly where we left off. And it's deterministic, right? So it preserves sample order between checkpoints and resumptions. And then when it works in tandem with Composer, it kind of works with the checkpointing system very seamlessly. So basically everything is vertically integrated. So everything on top there, everything above deep learning libraries is open source. You can go check out the streaming repo. You can go check out the Composer repo. And that's actually what we refer to our training runtime. Everything below that is actually our paid product, which I'll kind of talk about next here. But this is, to actually basically have a great stack, we have a great training stack. We have to actually have a great platform to run it. And so this is really what's responsible for running and orchestrating and scheduling jobs. So basically, the platform architecture is actually built in a way that we've split it into basically two planes. The Mosaic control plane, it's actually cloud agnostic, and it manages all the multi-node orchestration, scheduling of runs. It does live real-time monitoring for faults and implements and works very, integrated very well with Composer and the training stack to do automatic recovery of runs when there's some type of hardware failure. The control plane can run and be deployed anywhere. And that's what allows us to actually focus on putting the compute plane in any cloud, right? This is where your actual accelerators are located. This is where the training runtime will actually run. And this can be anywhere, right? Your cloud of choice. It can be an on-prem data center if you want it. If you want to set this up at home, I'm sure we can get that to work. The platform's completely stateless. So at least the compute plane is actually completely stateless, where data can be streamed in, but storage is ephemeral. We do not save your data. It's completely private. The other advantage we offer by being able to deploy where your compute plane is data never has to leave your VPC either. So if you have strict kind of data provisioning or data access requirements, this all is actually very friendly to that kind of enterprise space. And lastly, we've got a really great CLI, various options in terms of command line interface that lets you manage, train, submit different training jobs, different training configs. It's all also accessible via Python SDK, and we are building out our web console to actually have feature parity with that, but currently it's used for kind of account management, billing, and gathering usage statistics. So overall, it's a complete solution. We're a one-stop shop. So I think where we're at now is we've got a great model. We've got a great model architecture. We've got a place you can train it from scratch or you can fine tune it. What we really need now is a place to deploy it so it's usable. And so a few weeks ago, we actually announced our Inference infrastructure, Inference products. And this really is available now in about 2 tiers. So we have a starter tier, and this is your hosted API, right? So we have MPT deployments hosted that you basically pay for API usage after you sign up and are given access to the platform. And this is very price competitive. So I kind of put some of the pricing on the bottom right there. And the other thing we also offer is an enterprise tier, where let's say this hosted model isn't enough, you need to do some customization, or you've played with it, you've started entering your pipeline, you actually want to go and train your own model. That's where you kind of upgrade to the enterprise tier, and this offers some of the same benefits as the training stack, where you can deploy on your own private network, you can deploy on any cloud. And kind of handle all that infrastructure for you. You basically just pay per GPU, so it's a very, very scalable and understandable pricing model. And yeah, basically same privacy advantages. We do not save even for the starter tier. We do not save and train on your data. So yeah, that's kind of a very, very core tenet, I think, to what we built out, right? Is data protection and privacy. And yeah, what's to come? larger, better, interesting models. Definitely check out our open source tooling. We have a whole burst of announcements coming up, so stay tuned. Join our community Slack on social media. Please get engaged. We love the open source community. You guys, just everyone has done a fantastic job of finding issues and making feature requests, and we do our best to kind of handle them as fast as we can. And sign up for the MosaicML platform if you think that you can start using this and it'll meet your needs. So I think with that we can open it up for any questions.
Awesome. I've got a few, and then maybe we can kick it to roundtable. The first one I'd be curious to hear about is how do you guys think about training from scratch versus fine tuning? Is there a big difference there? Is that largely the same under the hood? Do you recommend one versus the other for certain types of clients? Yeah.
Yeah.
You want to take it, Dan?
Sure. Yeah. I think there's again, with a lot of these questions, there's still a lot of science left to do to figure out the right answer in every case. Generally, though, it kind of depends how much data you're showing up with. If you're showing up with enough data to do a training run from scratch, it's often something worth trying, particularly if you're kind of in a very different domain. So maybe the most extreme example is if you're showing up with a language that's not English, like Arabic, and you're going to want to train your own tokenizer, then if you're doing your own tokenizer, you have to start from scratch. We don't currently have any ways to kind of adapt the model to a new tokenizer. If you're showing up with kind of a smaller fine-tuning set of either unlabeled or labeled data, then you're going to probably want to be starting from a base model. The other answer is that you build, right? So do the cheapest thing first. If you have a small data set, start with a base model, fine-tune it, see how that does. Because one of the most important things here, right, is you have to actually try the model on the thing that you care about. And so do that as quickly as possible with the cheapest possible option, and then start scaling up to maybe training from scratch, maybe larger models, and stop when the thing is good enough for you. There's no reason to spend extra money and time if it's solving your problem.
Awesome. And then one other question I have for you guys is just on the difference between training and inference. Where do you think there's the most improvements for both you guys and the industry as a whole to kind of make progress? Is there more work left to be done on the training side or on the inference side of the infrastructure part?
I think at a high level, I think the answer is both.
Just if you had to choose one,
it's hard. So training definitely have a lot of, if you go back to the days when we were doing pure algorithmic research, right, and some of the stuff that we did with ResNets and BERT and Deep Lab, for example, and just bringing out those costs. We think, obviously there's a lot of room for improvements in terms of how you're training LLMs. You see this constantly. Some of our speed up methods we get on Twitter, right? Someone will post, "Hey, I flipped this flag and I got a 10x or 10% improvement or something," and we get on that really quick. So training definitely a lot of low hanging fruit, but also a lot of research to do in terms of efficiency and bringing the cost of compute. It's hard for me to decouple those two, and I think that is a mistake that people make, right? Where, okay, let's say you go and train 100 billion parameter model. The problem is deploying that at scale and making so people can use it. You can't decouple. You just can't decouple that picture, right? And so that's one of the hardest things is if we have someone come in that says, "Oh, I want to go train a trillion parameter model," it's okay. Even if you have the data, it's well, why? Because how are you going to host that, right? How are you going to deploy that? And for some very, very niche cases that might be possible. But generally, a lot of people, we don't think really need that, right? So I think what Daniel was saying earlier is probably the way to go is you start small, and the benefit of starting small is that you can iterate quickly. And yeah, maybe, you don't get the thing that you want right away, but I would argue you probably don't know that right away, right? You kind of it's a discovery process. So you start with what's been built, iterate on that. If you see value in pre-training, pre-train, but also don't forget about inference, right? And so I think even in inference, hosting large language models, there's a lot we can continue to do, right? There's a lot of interesting things going on in research in terms of how to compress large language models or distill them down into smaller models so they're cheaper. So if I had to pick for this, I'll choose training, but I do think it's hard to decouple the two. There's like a yin and yang scenario going on there.
I think also probably for the parts of inference that you can decouple from training, it's a bit easier to work on. Like you need less resources. You don't need a giant cluster to work on inference efficiency. So I think we've seen a lot of great work from the open source community there with like GGML and Llama CPP and all of that.
Reminder for people to add questions to the question box. I'll go there after one more. I wish Brandon was here for this, but I think he's having some internet issues. But I guess my question is like a lot of what both of you guys talked about was the tooling around these models. And so my question would be like, what is the tooling that you guys have built that you think is like most novel and you're most proud of? And then what is one piece of tooling that that doesn't exist in your guys' platform currently, but you wish someone, like maybe you guys will build this in the future, maybe you wish someone would build this, like one external piece of tooling that you think would be really valuable and needs to have kind of like more attention paid there?
That's a good question. I mean, I think that probably the most novel is, I mean, to me, I think it's probably streaming. In that, you know, it really kind of frees you from cloud and vendor lock-in. You can put your data somewhere, you can move it around. There's pricing and costs associated with doing all that, but you can calculate that, right? That's an understandable model. Whereas previously you had to co-locate, you know, your data with your compute, you were tied in. So I think, yeah, that's why I think tooling is actually great, because it unlocks you from clouds, and really what you want the clouds to be doing is a race to the bottom, right? They need to be competing on pricing and offering you the best cost per GPU. So giving open source and ourselves, anyone who needs to pay for compute, that type of leverage, I think is probably what makes streaming great. I want to see what Daniel says and then think about what I have a long wish list. I'm wondering what I should ask for if I have this.
I can take a stab at my wish list item. So I think one of the things that we and the community have been struggling a lot with is evaluating these models robustly. You know, you run the academic benchmarks, you get some numbers. Who knows what that means? You try out the model, you play with it for a little bit, and like ultimately has their own little internal tests for these models and deciding which one's best for their use case. And some of that is unavoidable, right? Like different models are going to be good for different things, and there's really no like substitute for just like having a little test set and looking at it and seeing what happens. But I would love to see more tooling around kind of evaluating the different aspects of the model that we can automatically, robustly evaluate, even if they're not, each one individually is not like the be all end all of model quality. Any like discrete, accurate points you can get on model eval is very helpful and kind of reduces the iteration cost of just like checking the vibes, as we say. So I'd love to see like more robust tooling for evaluating these large models.
So that's a great one. I think I know mine, which I think, you know, I have a former hardware background, you know, and I come from one of the hardware chip companies as well. But where is anyone else but NVIDIA for training, right? I think that's what I'd love to see. Like AMD had some great announcements yesterday, you know, MI300A, MI300X. We want to use it, right? Like we're ready. We love NVIDIA, don't get me wrong. They make amazing stuff, and we, you know, I think there's also other companies out there making amazing things. There's a, you know, a very robust and thriving hardware startup ecosystem. You know, I want to try some new hardware and really optimize them as a platform on different things. And honestly, my hypothesis is that different hardware will be good for different types of models as well. You know, this is actually something that we talked a lot about at the beginning, early days of Mosaic. Like, does it make sense to train LLMs on TPUs versus GPUs, or does it, you know, where is the best place to do this? And it kind of gets into the hardware, like in a lottery ticket type thing. But I think basically, hardware lottery type thing. But yeah, we want to run on more hardware.
Awesome. So the uploaded question is very similar to what you were talking about, Daniel, and it's around evaluation, and it ties in a little bit of I think it's combo kind of like Mosaic and then also some tie into LangChain. So let me try to parse this and turn this into some question. But basically, yeah, is there a systematic and quantitative approach to determine the most suitable open source pre-trained LLM for a specific use case, such as like document question answering in a particular domain? So that's one of the main like chains that we have. And so there's some stuff that he mentions as being inside LangChain, and I'm happy to talk about that. But yeah, I guess like building on your answer before, and yeah, like, and I think you said something really key about like having having a test data set of sorts. And so like, yeah, as you go from not these like academic benchmarks, but your particular task, like what does a good workflow and yeah, what does a good workflow seem like to you? And I'll take a stab at this after as well, but curious to hear your guys' thoughts.
Sure. On this. Yeah. So I mean, unfortunately, the answer is like sort of no. There is not a current good like systematic quantitative, but the more like if you have an enterprise and a bunch of people to label data and evaluate and stuff, at the end of the day, you just like, hey, you have to create a test set that is what the thing that you care about. And if your test set involves something that you can't automatically evaluate reliably, so if it's like open-ended generation, you have to evaluate it with humans. There are some approaches, like there's automated metrics that you can start with, and then there's like you can maybe evaluate with like GPT-4 or something like that.
Yeah, I was going to ask about that. What have you done that before? Have you seen that work?
We've definitely played around with it, and I think it definitely is like a signal that you can use in your evaluation. But for me personally, like I just don't at this point trust evaluating models with models. It's a good like read, like it probably gives you like some information, and since it's automated, you can do it more frequently perhaps than human eval. But there's both obvious biases, like there's a paper showing recently that like GPT-4 eval is biased to the position of the answer choice, and then I'm sure there's a bunch of harder to detect biases hiding, and so at the end of the day, like if you want to evaluate something hard, it's still humans for me.
Yeah. So the rest of the answer mentions some like things related to LangChains. So there's like a QA eval chain, which does the OpenAI or it uses a model to grade it. GPT-4 being the one that most people use in practices. It mentions auto evaluator, which is a way to do QA specific evaluation that like Lance Martin put out. And then there's a question about, yeah, what, and I guess let me reframe this. Like, how do you get this test data set? So like you mentioned this test data set, how do you get that?
Yeah.
And I guess like what should that look like? How many data points? What are characteristics of the test data points, so to speak?
Yeah, it's hard to answer in a general way, perhaps, but I think people tend to shy away from just like spending a couple days writing data, and that can actually be a great way to do it. Like if you sit down with your task and like take a couple days, you can write a reasonable amount of test data, or you can play with your model for a reasonable amount of time and kind of find the bounds. So I think don't shy away from, as Brandon talked about a lot, like looking at the data and perhaps even writing some data. Yeah, so like the tooling that you mentioned is great and helps you get some idea of the performance of the model, and then building tooling to make your like evaluation easier. So like A/B testing or something like that, just like a tiny little UI can be very helpful. But yeah, then like don't shy away from looking at and writing and data. Like those tasks are important.
Yeah, I mean, in a way, I think it's similar to writing unit tests for software, right? Like everyone kind of probably hates doing it, but it's critical, right? It's necessary. Otherwise, you have no idea if you have working code. And I think it's a little similar here. Like even when customers come in, right, and they say we want to train our own model, the first thing is, one of the first questions I think even our researchers or anyone asks is, how are you going to eval it, right? How are you going to know that this model is doing what you want it to do? there's a lot of frameworks out there, right? There's a lot of different eval suites out there that give you some idea of its performance in different domains. But at the end of the day, like you're using the model to do something. You are the domain expert, right? And so somehow, right, do what Daniel's saying, like go build your own eval metrics, go build your eval sets, spend time on that. Think about it as unit testing, because otherwise you're not going to know, right? There's no way you can scale it.
There's also a work I'll mention really quickly that's more from the kind of BERT era, and I'm not sure if it's been kind of extended, but it's called Checklist, and I think it was like a best paper at ACL or something like that. And it was about like how unit testing these models in some form. I really enjoyed that paper, so I encourage people to check it out.
That was a good one. That perfectly answers another question, or not perfectly, but there's a question about open source leaderboards and which ones are kind of like best. And I think the point around just having your own leaderboard is probably, irreplaceable for
look at all of them, take them all with a grain of salt, and like nothing compares to evaluating all the models in your own framework so that you know the exact same thing was run.
Yeah. This might be a can of worms, but honestly, I think a leaderboard out there that is actually like, here are all the different things that we've tuned a model to do, right? Is like a lot of these are like, here is a currently trained model and here's how it performs in verticals. But really, like, that's important, but also it's not clear to me that speaks to the versatility of a model, right? And like, what does that even mean? And so yeah, I'm really curious, like, and I think I was looking for sources for this presentation of community project with MPT, but very curious, like what sort of different verticals people are using MPT in, because that to me is adaptability and versatility, right? Not just, oh, it's great at these things currently, because we kind of want people to be fine tuning it. And we want people to be modifying it for their own use cases.
Awesome. We're running up on time, so I'm going to combine the last two questions into one and maybe give you guys a final chance to talk about Mosaic. So the combo question is basically, how can open source communities and pre-revenue startups, so very cash kind of like constrained and resource constrained, how can they use MosaicML to train their own custom models? And combining with the other part, are there best practices that you would recommend for them doing so?
Oh yeah, sure. I mean, first and foremost, start using our training stack, right? You can use that on your 3090 or 4090 workstation at home. If you have problems, ping us. Daniel and I, everyone on the team is very, very responsive on our community Slack. I think we're creating a community Discord soon, but join our community and tell us your issues. File them on GitHub. And we'll fix them for you. We love working with startups. We work with a lot of startups. We are a startup, and so that's the best way. When you decide you want to scale your compute up, what's great is obviously sign up and reach out to our sales team or just ping us on community even, and someone will get in touch with you. And the best part of using the stack is, if you've got it working on your 4090, you can easily scale it to multiple GPUs or multiple nodes, hundreds of GPUs when you start running on the platform. So there's a very seamless kind of transition plan there. So you don't have to reinvent every way. Just start with our open source tooling, and it's a natural entry point into our kind of platform, which you're going to use more at an enterprise scale.
Awesome. All right, we're going to end it there. Thank you guys for joining. Thank you, Brandon, for joining earlier. I'm glad we got the presentation in before his Wi-Fi cut out. So overall, hope this was a deep dive into open source LLMs. Still a lot of questions in my mind, and I feel like the field is progressing so rapidly. I don't know how you guys kind of like keep up with it. So, but thanks for joining. Thanks for continuing to push on it. I think we all agree that the more open source LLMs, the better. So, all right.
Thanks for hosting this.
Thanks so much.
See you guys.